Thanks also to the organizers for inviting me here. And I want to speak about joint work with Radek Erban, which we started when I was visiting him a couple months ago. And he actually told me about a series of experiments done by biologists with these beautiful animals. These are desert locusts, and as you might know, there are these locust outbreaks where huge flocks of them fly and they just eat everything what they see, so they can cause a big damage to agriculture. So there is an interest of understanding the flocking behavior of these locusts, and maybe at one day we will be able to prevent them in flocking and making this big damage. And one of these experiments was done in 2006, where they took locust nymphs. I'm sorry. What is the locust nymphs, which actually do not have wings yet, so they do not fly. They just run or march, and they put them in a ring-shaped arena. You will see in a second what does it look like, and they made two fundamental observations. So the first was that as they increased the density of the locusts in the arena, they observed the transition to highly ordered movement inside, and there's a beautiful video about that. So this is the ring-shaped arena. There's this outer wall and this inner wall, and they just run inside. So this is like 2 meters in the diameter, and the camera is just above the arena. And so you see that basically 80% of the locusts, they run in a counterclockwise direction. There are some which try to run in the opposite direction, some trying to hit the wall, some are sleeping or maybe are dead. But on average, most of them run in a highly aligned fashion in the counterclockwise direction. So this is the first observation. And the second is that time to time, the whole group switches the direction. So time to time, from counterclockwise to clockwise or vice versa. And the mean periods between this switching is actually increasing with increasing the number of locusts in the arena. And actually there is a mathematical model which at least qualitatively explains this behavior, which is the 1D Vichek-Chirov model. Interestingly, it's older than the experiment itself. And Yates and his colleagues, they wanted to find a quantitative match of the experiment with the observed data. Actually, they found that it's not possible with the original Vichek-Chirov model, and they proposed a modification. I cannot go too much into details, but the essential point of the modification by Yates is that the individuals appear to increase the randomness of their motion in response to loss of alignment of the group. Meaning that when you observe that the alignment is lost, you start to be more nervous, you start to move more around and change the directions. And this seems to help the group to find a new ordered state more quickly. Actually, this was the starting point of our work, because we said, okay, let's try to design a possibly simple model which would be just stochastic, and the stochasticity would depend on the alignment or disalignment of the group. So the model is the following. We consider the group of n locusts or agents running in a 1D torus, which we identified with the periodic domain, periodic interval 0, 1. And so everybody is running with the same speed, which is 1. And you either run to the left or to the right, clockwise or counterclockwise. And then everybody is observing what the others do in the neighborhood. So mathematically, we define the local average velocity, which is actually the normalized weighted average of the individual velocities. The weight depends on the mutual distances. And by the normalization, you get that this UI log is always between -1 and 1. And W is a weight function which you can choose quite arbitrarily. It just has to be bounded and non-negative. and actually has to be strictly positive in 0, such that this normalizing factor always is strictly positive. So UI log is always well defined. And the standard choice would be that W is a characteristic function of some interval 0R, which corresponds to some finite sampling radius. This is, for instance, the choice in the Vicek and Chirok model. And the point is that everybody time to time switches the direction from -1 to 1 or the opposite. And the switching is random, directed by a Poisson process with the rate gamma 0, which is just a non-negative constant corresponding to some intrinsic noise in the model, plus a term which describes the tendency to alignment or disalignment. So, for instance, when everybody around you is running to the right, then this term would be 1, and you are running to the right as well, then this difference is 0. So your switching rate would be then just gamma 0, the intrinsic noise level. While if everybody is running to the right and you are running to the left, then this difference is almost 2, and then your switching rate or the probability that you would switch is higher, and this gamma 0 plus 4b. So the switching rate for every individual is always lying between these two values, and if you observe that you lost the alignment with your colleagues, then you just increase your switching rate. And that's it, that's the model. And I would like to point out that basically the difference of this model to the standard flocking models like Vicek-Chirok and others is that usually in these models we have a deterministic term which describes the tendency to alignment plus some noise, while here we have just the stochastic, just the, let's say, random switching, and we just increase or decrease the stochasticity depending on the alignment or disalignment of the group. So I would say the model is somehow more primitive in a sense, or more phenomenologically simple. So let's see if with such a simple model we can actually explain the experimental observations. So this is just some numerics done with the model where we observed the long time statistics of the group mean velocity, and we use 5, 9, and 15 locusts, and you see quite clearly that with 5 locusts there is no preferred direction of movement of the group, so they basically they choose the group velocity just in this fashion. While when you increase the number of locusts, you can see that you start having 2 preferred states. So this state is corresponds to the state when like 80% of them run to the left and the rest runs to the right, and this is just vice versa. So this is the first experimental observation that when you increase the number of locusts, they start to run in a ordered fashion. Then the second observation was the switching behavior, which we can actually analyze systematically using the Fokker-Planck equation. But to derive the Fokker-Planck equation, we have to restrict to the case when the weight W is just a constant. So then all the local mean velocities are actually equal to the same global velocity for the whole group. Then you just write the Fokker-Planck equation for the system. And the point is that the steady state solution of the Fokker-Planck equation describes the long time statistics of the system. I will show you a picture about that later. And we can actually write the steady state solution of the Fokker-Planck equation explicitly. And when you look at it, you can distinguish the 2 cases. So when gamma 0 is bigger than b times this constant, then the system prefers to be in the disordered state, u equal to 0, while this is the large noise case, while in the small noise case, when the intrinsic noise is smaller than this threshold, you have 2 preferred ordered states, symmetric, so they are plus minus us, and us is either 1 or is lying inside the interval minus and 1 depending on the choice of the parameters. And I think this picture explains this very well. So this is the first row is the high noise case and the second row is the low noise case. And so here you see the preference of the disordered states, u equal to 0 or u being close to 0, which means that more or less half of the group goes to the left and half of the group goes to the right. And here you can see the time evolution of the system, while in the low noise case you see the two preferred states. Actually this line here is the steady state of the Fokker-Planck equation, and these lines here are the histograms of the long time observation of the system. And so you see the corresponding time evolution is that the system stays in the one aligned state for a while, then it switches to the other direction, then it switches again after a while, and so on. And the point is that we can even derive an explicit formula, or estimation of the mean switching time, which can be derived by the Kramers theory. The formula is not that important, but the important thing is that the mean switching time grows exponentially for growing n, and this seems to be with agreement with the experimental data. The usual problem is that you don't have enough data, but so from the experiment, this is the number of locusts versus the mean switching time in logarithmic scale. So you could quite say that the mean switching time behaves exponentially, and this is just a snapshot of the time behavior of the system, time evolution of the system, and I'm just showing that to basically tell you that at least qualitatively the picture looks very, very similar to the numerical results which we had. So it seems that the model is a reasonable and interesting model to study, and the point why I am speaking here is the following. Let's now go back to the stochastic discrete system. Let's forget the Fokker-Planck equation, and let's forget the restriction that the weight W is a constant. So now we can consider general weights W. We just need that they are bounded and strictly positive on some finite interval around 0. And then we just write the Liouville equation for the system. So Pn is the probability of being in the state x1 v1 to xn vn, and we want to derive the mean field limit. So we define the k particle marginals by integrating and summing with respect to n minus k particles, so particle locations and velocities. And then we marginalize the Liouville equation. Actually takes a little bit of work to compute the marginals of the collision terms. But after you do this, you come up with this BBGQI hierarchy. So this is a system for the marginals P and K. But you maybe already see a problem here. We also have some marginals which I call Q and R here, and these are actually, or can be seen as moments of the probability distribution Pn with respect to the velocity u, which is always given by the normalized weighted average of the individual velocities. And so now the usual procedure would be you pass to the limit n to infinity, you make the molecular chaos ansatz and so on. But the point here is you can at least formally pass to the limit in this Q and R, but then you don't know what is the relation between the limit of these two with the limit of P. So it's not even clear how you would make the molecular chaos ansatz after passing to the limit. Or in other words, you can say that the system of these moments is not closed. Okay, so I didn't see and I didn't found any other way than cheating, in the sense that we make the molecular chaos ansatz even before passing to the limit n to infinity. So we take the Pn in this factorizing shape, where P is the one particle marginal. And this can be actually seen also as a moment closure assumption, because then we can express the moments Q in terms of Q and R in terms of these one particle marginals P. And now we may try to pass to the limit n to infinity, which means to pass to the limit here, which looks quite messy on the first side, passing to the n to infinity here. But the point is that you can rewrite the expression defining the what I call mass density. So this is the sum of those who go to the right plus those who go to the left, and the flux. And the point is that for every t, this rho is a probability measure, and then you can understand this w as a random variable with respect to the probability measure rho, and use the law of a large number, which tells you that the average goes to the expected value of w. So when you use this, you can show that the limits of q and r are always the product of the first k particle distribution functions times u and u squared, where u is just the average flux divided by the average density, which I think pretty much makes sense from the modeling point of view. So this leads then to a kinetic system for, I now denote P plus, the density of those who run to the right, and P minus of those who go to the left. And then we have a coupled system of equations for P plus and P minus, which you can actually understand. The term on the right hand side for P plus, this is a loss term due to those who go to the right and turn to the left. And this is a gain term due to those who go to the left and turn to the right, and the same is for P minus. There is a problem with the definition of U, but maybe I show you first the corresponding hydrodynamic system, which is derived very easily. You just write the system in terms of rho, which is P plus plus P minus, and J, which is the difference of them. So then you have a mass conservation and momentum non-conservation, I would say. And again, U is the average flux divided by the average density. But the point is that it can very well happen that the denominator here is 0, because there might be places where there is nobody there, so rho is 0 there. But so in this case, we cannot define U correctly. But the point is that we do not have to, because due to the properties of W, so if you are on the set as 0, where the denominator is 0, you know that rho would be 0 as well, and J, because it's always strictly smaller than rho. And when you look at the equation, you always have the product of U times J or U times rho. So whenever U is not defined, rho and J are 0 anyway. So the product of U and J and U and rho is always well defined. Concerning existence of solutions of this system, one point is that we have global L infinity estimates. Then when we regularize the formula for the velocity by adding a small epsilon to the denominator, actually because this is like a convolution operator, it is equicontinuous and bounded, so showing existence of solutions with this regularized velocity is easy, and you get the compactness by the Arzela-Ascoli theorem. And then you pass with epsilon to 0, so it's easy unless in the nonlinear terms. But it's also not that difficult here, because basically you divide the set omega on the set where ui is going uniformly to u, because the denominator is strictly bigger than 0, or rho and j are going to 0, and then you can pass to the limit in these two terms. So this is concerning existence of solutions. Uniqueness is an open problem, because basically this system is not really a physical system. So far we were not able to find any entropy or anything, any decreasing functional for the system. So uniqueness and convergence to equilibrium is an open problem. And actually one can formally choose the weight W to be a Dirac delta. So in this case, you remove the non-locality of the system, then U is just J over rho, as is usually the case, and then you just get a nonlinear system like this. And this actually corresponds to shrinking the interaction radius to 0. So you can take solutions which have the weight like a characteristic function of the interval 0r, and when you shrink r to 0, you obtain the velocity, which is just J over rho. So this is connected to the question, what happens to the discrete system actually when you shrink the interaction radius to 0. So we again jump to the beginning, to the discrete stochastic system, and what we can show actually, if you consider the shrinking of the interaction radius, so W is again a characteristic function of 0r, and when you shrink the interaction radius as 1 over n, and then let n to infinity, you obtain a new kinetic system where in place of u, which before was j over rho, you have j over rho times this factor depending on rho. So this is like sort of slowing down. When rho is small, you are slowing down everything. And in place of u squared, you get j squared over rho squared times the same factor, plus this ugly term, which I do not like too much, because this function g actually cannot be expressed in closed terms. So you either get this formula as an infinite sum, or actually it's sort of it's related to the so-called exponential integral function. So this is the best description of g we can get. And yeah, I think it would be very nice if this term was not here from the modeling point of view, but unfortunately it is. And what we also can show that this limit actually, or this way of shrinking the interaction radius is the significant one, because if you shrink faster than 1 over n, for instance like 1 over n squared, then you get a system where you have no interactions, meaning that u and u squared would be both 0. On the other hand, when you shrink slower than 1 over n, for instance like 1 over square root of n, then you get a system which was on the last slide. So a system where the weight is Dirac delta and u is just local j over rho. Okay, I think I still. Yeah. So we already have like 3 models. So one with the regular weights, one with the singular weight Dirac delta, and one with obtained in this significant limit. And now we'd like to speak about, or make a short note about the long-term behavior. So in the case where you use the regular weights W, we can only conjecture based on numerical simulations that rho and j always converge to some constants. So rho would be actually 1, because the total mass of the system is 1, and j is some constant which we do not know how to identify. And if we are in the high noise case, gamma 0 bigger than b, actually the asymptotic state for j is 0. So whenever you have the high noise case, you end up with zero flux everywhere. And so this is only a conjecture, and we only have the proof in the case where, again, the weight W is a constant, and you are in the, let's say, very high noise case where gamma 0 is bigger even than 2b. The point is that when W is a constant, you can write, you can integrate the equation for J, for the flux, to get just the ODE for the global mean velocity u, and based on it you can, well, this is now interesting because you can show that this ODE has always steady state or stationary point u equal to 0, and this is stable if and only if you are in the high noise case, which means that when gamma 0 is bigger than b. If you are in the low noise case, gamma 0 smaller than b, then this steady state u equal to 0 is unstable, and you have 2 other steady states which are symmetrically about 0. So again, this phenomena of high noise and low noise case also translates here. And based on the information, then when gamma 0 is bigger than b, you have exponential decay of u to 0. We can actually prove that j is going to 0 in the L2 sense when t goes to infinity, but we need the additional assumption that gamma 0 actually is bigger than 2b. All the other cases are open, but always when you make the numerics, you end up with constants, and if gamma 0 is bigger than b, you end up with j equal to 0. The case where you use the singular weight, so W is Dirac delta, is more interesting, because then it's actually better to describe the system in terms of this p plus and p minus, which are the density of those going to the right and those going to the left. And so numerically, you see, you always end up with a traveling wave solution solving this system. And so when you assume that you have your solution solving this system and you are in the equilibrium such that the right hand side in the kinetic system equation for J is 0, you can show that either p plus or p minus must be globally constant, and the other, which is not constant, must be piecewise constant with only two values, and the values are given by this expression. So for this case, I want to show you the numerics. So this is p plus, p minus, rho, which is the sum of them, and j, this is the blue line, this is the difference of them, and u is this is the green dashed line. And so we start with a setting where you have a bunch of those who go to the right and bunch of those who go to the left, and the initial conditions for p plus and p minus otherwise are 0. And then when you let it run, you see that yes, these are marching to the right, these are marching to the left, and every time they meet, those who go to the right increase a little bit, and those who go to the left decrease a little bit, which is caused by the fact that initially we had more of those going to the right, and after a while you end up with the situation where those going to the right actually won. So we have so p plus is jumping between the two constants, as I showed before. P minus is a global constant, and this is the traveling wave solution. Okay, that's it. Thank you very much for being with me.